Hi goers, welcome to the Chapter 10 review video. This is the final video of Organic 1, so congratulations on making it this far. Don't worry, there's going to be a whole series of review videos for Orgo 2 if you're continuing on. And even if you don't have Dr. Peterson, still feel free to use these review videos for Orgo 2, or even you review these Orgo 1 videos for before you go in there. So let's just jump right in and get you guys done with Orgo 1. Okay, so this chapter is all about alcohols. This is chapter 10, and we're just going to really just talk about all these different types of classic reactions that we see with alcohols. We did just finish talking about SN1 and SN2 reactions, and I want you guys to be aware that there is a lot of SN1 and SN2 reactions involving alcohols, so we're going to build on that chemical logic that we talked about in chapter 9. Okay, so the first reaction is called alkoxide anion synthesis, and it's basically what an alkoxide anion is it's just the deprotonated version of that alcohol. So, if I see this, alcohol over here, it's really just going to be that. That is the alkoxide anion version of that alcohol. So the way that we do that is that we can take a base like sodium hydride, and that is a source of hydride anion, and that base is going to deprotonate that terminal proton attached to that oxygen and create the alkoxide anion. So, the result of that would be hydrogen gas. So you remember that from that step, you're going to generate hydrogen gas, H2, and also generate that alkoxide anion. So now that anion is sufficiently nucleophilic to attack an alkyl halide at the electrophilic carbon and participate in what it looks like to be an SN2 reaction in step 2. So recall that all these, chemical applications still apply, they don't go away. So this ethyl bromine looks like this. If I were to classify the substitution of that starting material, that most definitely is a primary alkyl halide. We see we have a polar aprotic solvent like DMF, so polar aprotic. And we have a very strong nucleophile because it's negatively charged, so I would expect the SN2 reaction. So now that negatively charged alkoxide anion is going to attack that electrophilic carbon that bears the bromine, facilitate the removal of the bromine, and we just synthesized an ether. So our end product should be something that looks like that. Okay? So this is our ether that we've created by synthesizing the alkoxide anion and doing an SN2 nucleophilic attack reaction with an alkyl halide. You can also generate this alkoxide anion in another way. So instead of using, sodium hydride, you can use two equivalents of pure metal. So we can either see sometimes two equivalents of sodium with a degree sign over it, or two equivalents of potassium. Sometimes you can do that, but in terms of mechanism, the sodium hydride makes the most sense to me. Okay, so the next reaction we're going to talk about is acid-catalyzed alcohol to haloalkane conversion. I know that's a long name. Basically, we're going to take these alcohols and subject them to these, acids, and we're going to protonate them. And there's a consequence of protonating them. So alcohols, as they are, OHs, are poor leaving groups. So, the best leaving groups are the weakest bases. So let's kind of rationalize why that is. So remember that nucleophilicity parallels basicity. So, we can say that the stronger the nucleophile, the stronger the base. So basically, strong bases like to attack, electrophilic centers. But weak bases, meaning that they're weak nucleophiles, don't like to attack and would therefore like to leave. So, when we protonate, so basically if I were to consider like maybe just an SN1 mechanism, like let's skip to this example over here, and that hydroxyl group were just to leave on its own, the result is OH minus. And that's a pretty strong base. So remember, we said like aqueous bases like sodium hydroxide, potassium hydroxide, those like to attack things. So, this is a very, very strong base, not a weak base, and it would be a very poor leaving group. So the role of the acid in this case, or it could be HBr, HCl, any of those strong bases, is to make this leaving group, or this hydroxyl group, a good leaving group. So right now it's bad, but by protonating it, we're going to make it a weaker base and make it a better leaving group. So we can rationalize the first mechanistic step, where if I were to redraw hydrobromic acid over here, the lone pairs on the oxygen are going to attack that hydrogen, making it protonated and generating the bromide anion. So we would expect basically OH2 positive on that wedge configuration, and we also generated that bromine. Okay, so now we have this choice. Is this, reaction going to go through an SN1 or an SN2 reaction? Well, our bromine is negatively charged, so that's a pretty good nucleophile. So I can just say good nucleophile. Okay, and then that, starting material is definitely secondary. So we see negatively charged good nucleophile. We see secondary, so that's that gray area. So, I would predict that this is going to follow an SN2 mechanism. So, the mechanistic arrows for this would be that bromine attacking and kicking off that protonated hydroxyl group as water. So then the result would be inversion of configuration. So it's important to note that bromine is now on a dash configuration because on our starting material that hydroxyl is on a wedge. And then we also generated water as a leaving group, and that is a weaker base compared to that hydroxyl group, and that's why this reaction can progress. That's why we use a strong base. So let's consider, a tertiary alcohol. So again, that same, mechanistic step is going to happen where that lone pair is going to grab a proton, generate the bromine anion. So the result of that would be, this protonated tertiary alcohol. So it looks like water. And then we have that bromide anion. So, yeah, we have a good nucleophile in this case, but that tertiary substitution pattern actually prevents, this nucleophile from directly attacking. So this is definitely going to be an SN1 reaction, okay, because of that steric hindrance. So that water can leave on its own. That's the rate-determining step. And we would get, that tertiary carbocation, and now that bromine anion can come in and attack. So this is consistent with an SN1 mechanism. So we would get racemization of our products. So we would expect both the wedge and dash enantiomer if this was in fact a chiral center, which it's not because there's two methyl groups. So you can see that we can have SN1 and SN2 interconversion depending on the substitution of our alcohol starting material. So primary and secondary will typically go through an SN2 mechanism, and then a tertiary will typically go through an SN1 mechanism. Okay, so the next reaction is phosphorus tribromide haloalkane conversion. And really what this is that phosphorus tribromide is just a source of bromine, and that's going to participate in only an SN2 reaction. So the next two reactions are only SN2 interconversion. So let's kind of just take an example of that. So, the first step is we have this secondary alcohol, and we have phosphorus tribromide. So we can rationalize that. It looks like this, the Lewis structure. And, that hydroxyl, although it's not negatively charged, is still a nucleophile. And remember, phosphorus can accommodate more electrons, so we would expect nucleophilic attack at that position. So the result of that would be something that looks like this. Okay, and don't forget that we exceeded, phosphorus's octet at that position, so we generated a source of bromide as well. And don't forget we have a protonated alcohol to start with. Okay, so then that bromide is going to do an SN2 reaction, an attack from the dash configuration to kick off that leaving group. So this would be a way to convert these alcohols into haloalkanes, more specifically the bromoalkane, because we're using this source of phosphorus tribromide. So we would also get HOPBr2 as a byproduct. Okay, so that is definitely consistent with an SN2 reaction. Then if I were to look at this next example, we have a tertiary starting material. So, remember, these are SN2 reactions. So once I generated that high energy intermediate, like at this position, that bromine is supposed to attack at that carbon that bears the hydroxyl group and facilitates its removal. But this is tertiary, so there's no way that we can do SN2 reactions with this. So therefore, there would be no reaction with this tertiary alcohol. It has to be, we're limited to primary and secondary starting materials. Okay? So then if we were to look at this, bromine over here, we can see that it's secondary, but it's on a wedge configuration. So, a way to manipulate that stereochemistry is to do a series of SN2 reactions. So this sodium azide is in DMF, that's a strong nucleophile because it's negatively charged. Polar aprotic condition, so I'm expecting SN2. So the result of step 1 would be the azide on a dash. And then step 2, it's also a SN2 reaction because we have a negatively charged hydroxyl and DMF, so I would expect the hydroxyl on a wedge. Okay, and then finally, with PBr3, remember that is an SN2 reaction, so I'm not going to draw the mechanism again, but you would expect inversion of configuration. So now, the bromine is going to be on a dash. Okay, so we would expect only that stereoisomer, but you can see we can do a series of SN2 reactions and, manipulate the stereochemistry of that haloalkane starting material. Okay, so there is one more type of, haloalkane interconversion, and that's with thionyl chloride, and you can rationalize that that's probably going to, may create a chlorine haloalkane instead of the bromine. Okay, so the Lewis structure of thionyl chloride looks like this. Okay, and that same, series of mechanistic points where that hydroxyl lone pair is going to attract the sulfur, and that's also going to, resonate those oxygen lone pairs up. So the result of that step, let me zoom in over here, is going to be okay, and what happens is that we need to generate some source of chloride. So these lone pairs on the oxygen can resonate down and actually facilitate the removal of the chlorine. So the result of these mechanistic steps would be and now that chloride can do an SN2 reaction with this high energy intermediate, and the result would be this haloalkane, and you generate sulfur dioxide and HCl as your byproduct. So you can see once this kicks off, you really have and what could happen is that, this chloride grab that H, then those lone pairs break in, and that breaks off. So you don't need to know this intramolecular, reaction that generates sulfur dioxide and hydrochloric acid, but just realize that our two byproducts are SO2 and HCl. So we typically see with, thionyl chloride this reagent called pyridine. And what pyridine is it's a, proton sponge. So it's supposed to counteract unwanted side reactions, due to changes in pH. So you can see that when we generate hydrochloric acid, so pyridine is going to soak up that hydrochloric acid to combat, changes in pHs. So basically pyridine you can rationalize as a base, and that base is going to soak up that acid to prevent any unwanted side reactions. Okay, so again, phosphorus tribromide and thionyl chloride are basically two types of SN2 reactions that are going to convert alcohols directly into a corresponding haloalkane. But keep in mind we do see inversion of configuration, which is consistent with SN2 reactions. Okay, so the next reaction we're going to talk about is alcohol to aryl sulfonate conversion. So this reaction is important in synthesis because we have retention of stereochemistry. So whatever that stereochemical configuration is of that, hydroxyl starting material is going to retain when we create the aryl sulfonate. Okay, so, step 1 is just going to be an SN2 reaction with that, haloalkane, and it's more specifically that chloride. So we would expect, the result of step 1 to be something that looks like this. So that hydroxyl group is going to be on a dash, and tosyl chloride and pyridine is the reagent that is responsible for converting that alcohol into an aryl sulfonate. You don't need to know the mechanism for this reaction, but you do need to know that we're going to retain the stereochemical configuration of that alcohol, so we would expect OTS. Okay, so that's the aryl sulfonate, shorthand notation, and that's the result of reacting with tosyl chloride and pyridine. Okay, so notice how the stereochemical configuration was retained, and then phosphorus tribromide, remember, is another SN2 reaction, so we would expect that bromine to come on a wedge. So, clearly here, if you wanted to have a bromine on a wedge, you had to go through this, tosyl chloride intermediate, or this aryl sulfonate, because we were to retain that stereochemistry. Okay. So then, dehydration of alcohols. So, in order to dehydrate alcohols, first of all, the first step is just this SN1 reaction, SN2 reaction. So we would expect, if there was any stereochem shown in the starting material, we would expect that hydroxyl group to come on, the opposite configuration, but there isn't any stereochemistry to consider here. And the role of that acid is to actually just protonate. So if I just drew the Lewis structure of this starting material, okay, so basically what that is that lone pair on that oxygen of the alcohol is going to grab a proton from sulfuric acid, generate the conjugate base of sulfuric acid, and we just converted, that alcohol into a good leaving group. Okay, so what happens now is that this is going to result in an E1 mechanism. So dehydration of alcohols occurs in an E1 fashion, where we're going to generate actually a carbocation intermediate. So let me just write E1. So that water is going to leave on its own, and we're going to get a carbocation intermediate. So it looks something like this. Okay, and remember, carbocation intermediates are susceptible to all of those rearrangements that we've always talked about in organic chemistry. So we would expect a hydride shift to make that secondary carbocation a tertiary carbocation. And then we can move one more time because we want to get to the tertiary benzylic position. So the result of that would be this tertiary benzylic carbocation. And then finally, that conjugate base of sulfuric acid, so HSO4 minus, so I'll just draw it like this. Is going to depronate an adjacent hydrogen, so this is the E1 mechanism, and donate that electron density in to form a pi bond. So we can dehydrate alcohols to form these pi bonds, like so. And the role of heat is to just facilitate, the removal of water to drive the equilibrium towards the right. So you can dehydrate alcohols by subjecting them to acid catalyst and, heat and facilitate the removal of water to generate these pi bonds. So that's definitely useful in synthesis. Okay, so the last reaction that you guys are going to learn in organic chemistry is the oxidation of alcohols. So depending on the substitution of your alcohol will dictate, what, end functional group you get. So if you have a primary alcohol, so basically the reaction scheme for oxidation is always alcohols to aldehydes and or ketones to carboxylic acid. So it's always that kind of flow. It's always alcohols to aldehydes and or ketones to carboxylic acids. And the reductions would go the other way, but that's an Orgo 2 topic. Okay, so, we can, manipulate where we're going to stop, either to the aldehyde or carboxylic acid for primary alcohols, depending on the strength of our oxidizing agent. Okay, so there are three types of oxidizing agents we're going to talk about, and the metal chromates, or sodium dichromate, which we see below, and we can see Na2Cr2O7, sometimes we see the potassium dichromate, and sometimes we see something called Jones's reagent. So all of those three reagents are very strong oxidizing agents, and those oxidizing agents, when given a choice, are going to go all the way to the carboxylic acid and not stop at the aldehyde or ketone, intermediate. Then the weak oxidizing agent, there's only one of them that we know, and it's called PCC. So that's the weak oxidizing agent. Okay, so when given a choice, that is always going to stop at the aldehydes or their ketones and not go to the carboxylic acid. Let's kind of just practice with that. So in this starting material, if we were to classify all these alcohols, we have a primary, a secondary, and a tertiary. So it's important to note that an oxidation, it's the loss of a carbon-hydrogen bond, but the gaining of a carbon-oxygen bond. So that is the organic definition of oxidation. So I'll just maybe write that out. So it's the loss of a carbon-hydrogen bond and the gaining of a carbon-oxygen bond. So that is the definition of oxidation in organic chemistry. So primary alcohols, and we know that this is actually a strong oxidizing agent because it's one of those chromates, so metal chromates, so strong oxidizing conditions. So primary alcohol, strong oxidizing conditions is going to take it to a carboxylic acid. Excuse me. For the secondary, we're going to go all the way to the ketone. There's no possibility to go to the carboxylic acid due to its substitution pattern. and the tertiary alcohol is going to have no oxidation reactions because of its substitution pattern. So if I were to predict the product, it would look something like this. Okay, so notice how that primary alcohol became a carboxylic acid, that secondary alcohol became a ketone, and that tertiary alcohol had no oxidation. Okay, so the reason why that tertiary alcohol can't have any oxidation is remember, we have to remove a hydrogen somewhere. So that's like the rule of oxidation, is losing that carbon-hydrogen bond, and there isn't any carbon-hydrogen bond on a tertiary position to lose, so there's no oxidation there. And then, for that secondary alcohol, there's only one hydrogen we could have lost, so we only can go to that ketone. We can't remove another hydrogen to, create that carboxylic acid. Okay? So let's move to, the weak oxidizing conditions. So we have PCC. So we definitely know that those are the weak oxidizing conditions. Typically, PCC is paired with like an inert solvent like dichloromethane, which is also called DCM. So if I were to classify these, we would have a secondary, and a primary. So no matter what the substitution is here, if it's primary or secondary, we're going to stop at the aldehyde and or ketone. So we would expect, a loss of stereochemistry. So that becomes, so you can tell that because it's primary, we're going to have an aldehyde. So primary yields aldehyde because there are two hydrogens here. And secondary is going to yield ketone because there are two R groups here, R and R prime, and there's that hydrogen there. Okay, so that's it. There's no mechanism for those. Just make sure you keep track of your strong and your weak oxidizing agent, and that is the end of Organic 1. You guys did it.